Okay, so in this video I'm going to be working through the method of characteristics, derivations, and problems from lecture notes 26. So if you want to follow along, you can open up the lecture note 26 from the 2015 lecture notes, and we'll be starting on what's labeled page 1, but it's actually the second page of the lecture notes. So the method of characteristics relies on the fact that for equations of a certain form, or for certain forms, it is possible to find a general solution and characterize the components of the original equation. Thus, for any equation which can be written in a characteristic form, it is possible to solve the equation by following prescribed steps. So, we'll start with the easiest example of the method of characteristics, which says that you want to find the characteristic equation for solutions of the form u of x and t equals f of x minus x naught of t. So we've looked at this before in class. This is just an advection. This is a solution to an advection equation, which means that you just have some solution, some shape, and it moves along the x-axis with time. But the x naught of t describes how this moves, and it's not necessarily a constant velocity. So, working backwards from the solution, we can characterize the equation that gets us there. So, taking the time derivative on both sides, we can get that the partial derivative of u with respect to t equals negative dx naught over dt times f prime, which then we say that f prime equals dxu, which is just kind of obvious from the way that we've written u and f, and then we'll call dx naught over dt v of x naught and t. So then that gives us that f of x minus x naught of t is a solution to, solves the equation the partial derivative of u with respect to t plus v of x and t times partial derivative of u with respect to x equals 0. So that's all that we're saying, which is pretty straightforward, and we've seen it before. This is just the general form of an advection equation. So now we can move on to a more complicated example, which we will look at section 1.1 of the lecture notes. So, the first time I read through these, I didn't really get what they were trying to get across, so hopefully I can shed some light if anyone else shares my confusions. So, basically, we're starting with the equation that we just derived above, this one right here, and we are going to add an ODE to it. So, the only thing you need to know is that v of x of t is going to be replaced with a of x and t. And so that means we are looking at equations of the form partial derivative of u with respect to t plus a of x and t times the partial derivative of u with respect to x equals this new term g of x, u, and t. So you can see that this can easily be broken up into two components. So we have our normal advection problem, more specifically with our typical advection term, and then we have a ODE term. So if you take this g and this, you end up with an ODE, and if you take the A and the T term, you end up with an advection problem. So what does that mean for us? Well, it just means that we are looking for solutions of the form u of x and t equals u of x of t and t. And we know this because this is a combination of advection and an ODE. So you have your typical advection solution, so just u of x of t, sort of like our f of x minus x naught of t, but then u also depends on t independently and will be changing shape because of the ODE term. So we can take the derivative of u with respect to t. So this is kind of hard to follow while I'm doing it, so I'll explain it after I write it all out. So we say that du over dt equals dtu plus dx over dt dxu. So you can think of the du over dt as the change of this u with respect to t. So that goes to that. And then this partial derivative, d sub tu, is the partial derivative of this u, the second u, with respect to this t. So this goes to here. And these arrows are getting all crossed up. But then the dx over dt, of course, corresponds to this x of t. And, wow, this is really messy. Then the u with respect, partial derivative of u with respect to x is talking about how u changes as you change x for a fixed t. So, okay, so by looking at this and the equation that we started with, we can see that they're exactly the same if we carefully rewrite our terms. So, as we did last time, we're going to say that dx over dt equals a of x and t. And then that gives us, so if we plug that into what we have, we say that du over dt equals the partial derivative of u with respect to t plus a, and then the partial derivative of u with respect to x. But if u of x and t gives us this, but is also a solution to this, that means that these two have to be equivalent somehow. So what we see is that this forces g of x, u, and t to be equivalent to du over dt. And that's it. That's the method of characteristics for this form. So for any equation which can be written as dtu plus a dxu equals g, which I'm sure we know from the p-sets is a lot of equations that can be written in this form, we know that this is simply an advection combined with ODE problem, and we know now that a of x and t describes how x moves with time, and we know that g x u t describes how u changes with t. So that means we can easily take this idea and apply it to different problems. So now I'm going to work through example problem 2 from the lecture notes. So the problem is that the partial derivative of u with respect to t plus 3 times the partial derivative of u with respect to x equals u. And of course we have the initial condition that u of x and t equals 0 equals f of x. So this is the most general initial condition that we could possibly be given. And that's it. There's no boundary conditions or anything like that. So we start by applying the method of characteristics. So we can quickly see that our g of x, u, and t equals u. And we can see that our a of x and t is just equal to 3. So the easiest thing to do is to start by solving for x of t, because that lets us see how our solution moves. So we know that a of x and t equals dx over dt. So then we know that dx over dt equals 3. So that's pretty straightforward. That's just a linear equation. So we know that x of t equals 3t plus an integration constant, which in this case we will cleverly call x naught. So then we say that x naught equals x minus 3t. And x naught is the x that we will be using when we solve for the ODE. So now our ODE is du over dt equals u. So that's something that we've also seen before, and we know that the solution to this ODE is that u equals a times e to the t. We know that our initial condition for t equals 0, so at t equals 0, we know that u equals f of x. So then plugging in t equals 0 into our u, we get that f of x has to equal a. But we already said that we are using x naught as our x, and the reason for this is because if we just use x, then we don't have anything that moves with time, and we know that the solution has to be an advection equation. So we're saying that, what we're actually saying is that f of x naught has to equal a. So this pretty quickly yields a solution u of x and t equals f of x minus 3t times e to the t. And we didn't take any big leaps of faith to get there. It just follows by carefully considering the initial conditions that you're given and everything that you know about the equation. So that's the method of characteristics. Hope this video was helpful. If I had a couple pointers to give, it would be that when you integrate, you have to remember to include your constants of integration, or else this will never work. The constants of integration are what allow you to combine the two results that you get. So if we had just said that u equaled e to the t, not a e to the t, we never would have been able to solve this equation. So thank you for watching, and I hope you found this helpful.